Let's take a look at a few theorems that involve parallel lines. And it's going to seem like these theorems that we're going to talk about in this video don't fit well with the other topics that we've gone through so far in this chapter when we were talking about parallelograms. But the reason why they are found where they are within the textbook that we use is that the proofs for all these theorems involve the ideas that we've been learning about with parallelograms. So that's why they're in here. We're not going to go through the proofs of the theorems necessarily, but I just wanted to kind of explain why these theorems kind of fit into the textbook where they do. Okay, well, first of all, let's talk about what parallel means. Let's remind ourselves that parallel lines are coplanar and don't intersect. Okay, we know that. We've been dealing with parallel lines a lot. In Theorem 5-8, it says that if two lines are parallel, then all the points on one line are equidistant from the other line. And so I have a diagram here that I'm going to try and use to kind of illustrate what Theorem 5-8 is saying. In this diagram, we have line M parallel to line N. And according to the theorem, if line M is parallel to line N, then every point on M should be equidistant from the other line. So here I have 2 points, C and D. The distance from C to line N should be the same as the distance from D to line N. And we've talked about before, if we're going to measure the distance from a point to a line, we're going to measure that distance along a segment that is perpendicular to the line that we're going to. So what this means in this diagram is, if M is parallel to N, then CG must be congruent to, segment CG must be congruent to segment DH. In Theorem 5-9, it says that if three parallel lines, so like I have here, I have these three parallel lines, if they cut off congruent segments on one transversal, then they are going to cut off congruent segments from any other transversal that goes across those three parallel lines. So what does that mean for this diagram right here? Well, if line KL is parallel to line NM and is also parallel to, those two are both parallel to line OP. So I have my three parallel lines. And if KN is congruent to NO, KN is congruent to NO, right? So we've satisfied the hypothesis of our theorem. We have three parallel lines that are cutting off congruent segments from this transversal right here. Then the theorem tells us that any other transversal that goes across those three parallel lines will end up with segments that are congruent. So in this case, that would mean that segment LM would be congruent to segment MP. So let's see how we can apply these things in an example problem. Given that line AR is parallel to line BS and is parallel to line CT, and RS is congruent to ST, complete each of the following. Well, first of all, we know that if those three parallel lines are dividing this transversal, if we're cutting off a couple congruent segments on this transversal, then it's going to cut off congruent segments from the other transversal as well, right? So if RS is 12, if that's a 12 right there, then ST we know is going to be a 12 because RS and ST are congruent. Okay, no problem there. If AB is 8, so I'll put an 8 up there, then BC, well, we know that AB and BC should be congruent according to the theorem that we just talked about on the previous slide. So BC would be 8. If AC is 20, so this whole thing is 20, then AB, well, if AC is 20, then AB would be half of that because AC has been broken into the two congruent segments. AB would be 20 divided by 2, or 10. And if BC is 6x, then AC from here to here, well, that would be 12x, right? Because we're going to have another 6x there, and if we go from A to C, it would be 6x plus 6x, which would be 12x. A couple more theorems that we can look at involving parallel lines. A couple more theorems. We have Theorem 5-10, which says a line that contains the midpoint of one side of a triangle and is parallel to another side will pass through the midpoint of the third side. So in this diagram here, you can see I have line DE. It contains the midpoint of side AC, right? D is the midpoint of segment AC because AD and DC are congruent. And line DE is parallel to another side of my triangle. It's parallel to AB. What the theorem says is if CD is congruent to AD in my picture like I've got marked, and if DE is parallel to AB, then that line DE should pass through the midpoint of this side. Well, what does that mean about my picture? It means that E would be the midpoint of this other side of the triangle, which would indicate that CE is congruent to EB. Then CE has to be congruent to EB. Theorem 5-11 says the segment that joins the midpoints of two sides of a triangle is A, going to be parallel to the third side, and B, going to be half as long. So in the diagram here, you can see that D is the midpoint of AC, and E is the midpoint of BC, and then I have this segment that's joining those two midpoints together. According to the theorem, if that's true, if CD is congruent to AD, and CE is congruent to BE, then what should be true is, first of all, ED should be parallel to AB. ED should be parallel to AB, parallel to the third side of the triangle, and the length of DE, so DE with no line over the top, remember that means the length of segment DE, should be half of the length of segment AB. So if segment AB was, for instance, as an example, if that was 20 units long, then DE would be 10. If it was 4x, then DE would be 2x. DE is going to be half as long as AB. So let's take a look at a couple examples that use these ideas. In this example, it says that X, Y, and Z are the midpoints of segment AB, segment BC, and segment AC respectively. Well, let's mark that on the picture so we understand that X is the midpoint of segment AB, so AX and XB will be congruent. Y is the midpoint of segment BC, so BY and CY are congruent. And Z is the midpoint of AC, so AZ and CZ will be congruent to each other. Well, if AC equals 24, so AC is 24, from here over to here is 24, then what is XY going to be? Well, we notice that segment XY is joining the midpoints of two sides of this triangle. It's joining X to Y, which are both midpoints. According to the theorem that we just learned, Theorem 5-11, the length of XY should be half of the length of AC. So if AC is 24, XY should be 12. Let's get rid of that. Sorry. Let's get rid of that information here, and let's take a look at the next problem. If AB is K, so from here up to here has a length of K, then YZ has a length of what? Well, again, this is the same situation. YZ is joining two midpoints of this triangle, so it should be half as long as the third side. It should be parallel to AB and half as long. So if AB is K, then YZ would be 1/2 of K, or K divided by 2. If XZ in this picture is 2y plus 3, 2y plus 3, then what would BC? Oops, I put that 2y plus 3 in the wrong spot, didn't I? Sorry, guys. 2y plus 3 would go right here. XZ, not XY. 2y plus 3. Then what's the length of BC? Well, again, same situation, right? XZ is joining two midpoints. So BC would have a length that's twice as big as XZ, or XZ would be half of what BC is, right? So BC would be 2 times 2y plus 3, which is equal to 4y plus 6, right? Distributive property right there. 4y plus 6 would be the length of BC. If AB equals 9, so now let's call this a 9. If BC has a length of 8, and AC has a length of 6, then the perimeter of XYZ, the triangle XYZ right here, would be what? Well, if AB is 9, then YZ would be half of that, which is 4.5. And if AC is 6, XY will be half of that, which is 3. And if BC is 8, then XZ would be half of that, which is 4. Perimeter is what we get when we add the three sides of a triangle together. So it would be equal to 3 plus 4 plus 4.5, which comes out to 11.5. So compare that. What's the perimeter of triangle ABC? If these were our measurements, what's the perimeter of triangle ABC? Well, triangle ABC would have a perimeter of 9 plus 8 plus 6, which is 23. What's the relationship between 23 and 11.5? 11.5 is half of 23, right? So the littler triangle formed by the joining of the midpoints of the big triangle has a perimeter that's half of what the big triangle's perimeter is. Let's see if we can apply that idea right here to question E. If the perimeter of triangle XYZ is 24, then what's the perimeter of triangle ABC going to be? Well, we just figured out that the little triangle has a perimeter that's half of what the big triangle is, right? So if in this question the little triangle has a perimeter of 24, the big triangle would have a perimeter that's 2 times 24, which is 48. Lastly, we have this example right here, where we have to name all the points that must be midpoints of the sides of segment ABC, or triangle ABC, I'm sorry. And what we know in this picture is that we know that CM is congruent to AM, right, because they're both 11, and that LM is parallel to BA. Now, according to theorem 5-11, if this segment right here is parallel to one side of the triangle, and it goes through the midpoint of another side, right? It's parallel to AB, goes to the midpoint of AC, then it's going to go through the midpoint of the other side. So I know that L must be a midpoint, that these two, that LC must be congruent to LB. So L is the midpoint of segment BC. Is there anything else that we can say? Can we say for any reason that N is the midpoint of AB? Well, I don't think that we can. I don't think that there's anything in this picture that would tell us that N has to be the midpoint. If we knew that this MN was parallel to this BC, then we could say that N is a midpoint, but we don't know that, right? It looks like they might be parallel, but there's nothing given to us that says that these would have to be parallel. So this is the only thing that we can say for sure, that L is the midpoint of segment BC.